Hello, and I'd like to welcome everybody to our analysis of WHO data to predict and explain life expectancy. I'd like you to meet the team. We are Tuan Lee, John Basora, Nitisha Kasha, and Mariam Teriharani. So first, I'd like to draw your attention to our outline, which has 6 distinct parts. First, our introduction, our data description, our scope and goal, our methodologies, results, and finally, our conclusion. I'd like to start with our introduction. And with that, I'd like to talk about population health. And it's a general human beings concern to care about their other human beings' general health. And by general health, we're going to measure that by life expectancy. Life expectancy is going to be our key performance indicator for assessing a population's general health. Demographic variables such as income composition and mortality rate can lead to greater life expectancy, we think. Additionally, immunization and human development index are often overlooked in life expectancy prediction. While this study is useful for government and NGOs, it also benefits insurance companies in evaluating existing and emerging markets at the national level. To study and predict life expectancy, a comprehensive data set is needed and was used. So let's start with our data description. We started with World Health Organization data, which was then combined with United Nations website economic data to have a final Kaggle data set for which we drew from. This data set had 22 variables, 2,938 observations, which had factors such as immunization-related factors, mortality factors, economic and social factors, which all contributed to the prediction of life expectancy. Now let's get down to the nitty-gritty of our data description. In our data, we have years ranging from 2000 to 2014, 193 distinct countries, 115% of them developed and 85% developing. We have vast populations, different levels of schooling, GDP per capita, as well as an income index from 0 to 1. We also have expenditure on health as a per capita of percentage of GDP. We also have general government expenditure on health, the BMI, alcohol consumption per capita, prevalence of thinness among children and adolescents, immunization coverage percentages of measles, diphtheria, as well as deaths per 1,000 in live births at HIV or AIDS, polio immunization, infant deaths per 1,000, under 5 deaths per 1,000, and last but not least, adult mortality, which is the probability of dying in 15 or 60 years per 1,000. And our target variable of life expectancy has a minimum of 36, a max of 89, and a mean of 68. And with this, I will turn it over to Natisha.
Thank you, John. Now that we have a basic understanding about the data, let's look into the problem statement. The main objective of this study is to understand the factors that are impacting the life expectancy. These factors can be related to the social factors or economic factors or the health related factors. So, this is the methodology that we have followed for the analysis. First, we started with exploratory data analysis, in which we have performed detailed analysis about each of the variables. Then we moved on to data cleaning. In data cleaning, we have performed things like handling outliers, missing values, and transformations. And coming to the modeling, we have performed 3 different models in this analysis. Moving on to the exploratory data analysis part, in here on the right, you can see the histogram of the average life expectancy of people. This graph more or less is normal. Here, life expectancy is our target variable. This graph shows the average life expectancy of people in developed countries and the developing countries. As you can see, the average life expectancy of people in developed countries is 79, whereas that of developing countries is 63. As you can see, there is a huge difference here. That huge difference here, that is 13 years. Now that we have a good idea about the average life expectancy in developed and developing countries, let's move into the trends in these two groups over the years. The blue line here represents the developed countries, and the orange line here represents the developing countries. As you can see, These two lines are more or less parallel to each other. This indicates that the trend over the years among these two groups is more or less equal. And the trend, as we can see from here, is increasing. So, based on the income compensation of resources variable, we have segregated all these countries into three different groups based on the income. That is high income group, moderate income group, and low income group. In high income group, the average life expectancy is approximately 76 years. In moderate income group, it is approximately 63 years, whereas in low income group, it is 58 years. As we can see that this is decreasing, the average life expectancy is decreasing as the income is decreasing. From here on, Mariam will continue.
Thank you, Nitisha. For the next step of visualization, a new variable named continent is created by using the country variable. Then 193 countries in our data have been grouped into their corresponding continents. And finally, the average of life expectancy is studied for different continents in the current figure. This figure demonstrates that the average of life expectancy is the highest among European countries compared to countries in other continents. It is followed by South America, North America, Oceania, Asia, and Africa, respectively. It also should be noted that the average of life expectancy in Africa is considerably less than the average of life expectancy in other continents. Additionally, continents' average life expectancy can be studied during the time. Starting 2000 and in 2014, all of the continents are nearly showing improvements in the average of life expectancy passing the years. Since during the time technology is developing and human beings are always trying to improve and facilitate people's lives, the result is convincing. The drop in North America starting 2008 and ending 2010 may be due to the Great Recession in 2008 and its consequences. Moreover, Europe has had a longer life expectancy at any point in time, and Africa has experienced a much shorter life expectancy than any other continent in all the years. The effect of GDP on life expectancy has been studied in many research, and its positive effect is truly justified. Let's see the impact of GDP and population on life expectancy in our research. GDP has been shown on the x-axis in the figure, and life expectancy has been shown on the y-axis. The size of the points is corresponding to the population of the country. As it is obvious, there is a very strong non-linear correlation between GDP and life expectancy. It is concluded that countries with large GDP values and low populations have a higher life expectancy. This slide includes a scatter plots showing if there is any relationship between life expectancy with BMI, with schooling, and with total expenditure. The left figure shows that BMI has a strong positive correlation with life expectancy, meaning that the more the value of BMI, the more the life expectancy. The middle picture is showing a strong positive correlation between schooling and life expectancy. It means that in a community with more years of schooling, the life expectancy is expected to be more. The left graph depicts the null relationship between life expectancy and total expenditure. Life expectancy and total expenditure are not correlated. It tells us that the change in the amount of general government expenditure on health don't affect life expectancy, and these two measures are uncorrelated. After EDA analysis, before jumping into modeling, data should be prepared. The first step of our data preparation is imputation. Missing values for the dependent variable, which is life expectancy, were much less than 1% of the data. So they have been removed. For the remaining values, variables were imputed based on the mean value of the special measure for each country. After applying these two imputation methods, there are still some missing values. It's because of having no records for a special measure for a country in different years. So countries with this issue have been removed. And finally, 133 countries out of 193 were kept in our sample data. Then we used histograms to visually inspect the distribution of our numerical variables and find out values for outliers if there is any. Some of the values seem to be potential outliers, but close scrutinizing the variables revealed that all could be easily explained and described, and their presence makes sense in the data. For example, an abnormally high number of measles related to an outbreak. So studying the candidates for outliers showed there is no outlier in our data set. The last thing is about transformation. Our target variable, life expectancy, has a reasonable distribution close to normal. Still, most of the other variables have been right skewed. And data transformation using log transformation was implemented on the mentioned variables to make the distribution closer to a normal distribution for the purpose of modeling. The next part, that is modeling, will be explained by Tuan.
Thank you, Mariam. So in modeling, the first step we go through is to partition our data. We choose a split of 80-20 for training and validation. As for modeling, we are going to go with three models. First is a regression model. We use it as a baseline. And then we have the neural network model and the gradient boosting model. For each of these model, we use two sets of variables. One is to use all the variables in the data set. The second is we want to use a reduced set of variables because some variables in our data have a multi-collinearity issue with each other. So we will look at them and exclude variables that have a VIF more than 10. Now, however, once we do this, what we have found is that the model using all variables have better predictive performance than the model using only selected variables. This is true across all three types of model. Next slide, please. So this is a result for each of these model in terms of predictive power. We look at the mean square error for the training and the validation data set. For the OLS regression, the training MSE is 13.28 and the validation for MSE is 11.68. So this is already the good performance. The R square with this model is over 90%. And now with the neural network, we were able to improve this even further with the training mean square error of 1.14 and the validation mean square error of 6.39. Our best model is gradient boosting model, and this one has a training mean square error of only 0.39 and the validation error is only 3.44. So looking at this model, we also look at the top 8 most important variables. They are HIV/AIDS, number HIV/AIDS deaths in 1,000 people, income composition of resources, adult mortality. This is also based on per 1,000 people. BMI is the average BMI for each country each year. Alcohol, teen is 9 years, under 5 deaths, and level schoolings. So in conclusion, we found that the gradient boosting model is the best performer based on our validation data. The model shows that HIV/AIDS is a very significant factor affecting life expectancy. This shows that this disease, this disease is still the disease of the century and is still a big problem in many parts of the world. This model is useful for each country government to assess their citizens' general well-being and the quality of their healthcare system. An interesting thing that we notice when we doing the EDA is that the total expenditure and the life expectancy don't have a correlation. Additionally, we recommend to use this gradient boosting model for any life or health insurance company that is considering the assessment of emerging and existing countries' market based on WSO data. And lastly, one of the interesting we found is that among the top important variables in the model, the only relevant economic predictor was the income composition of resources. And that is our presentation on predicting the life expectancy. Thank you very much for listening to our presentation.